right? So oxygen is, if it's elemental, the charge on it is -1. And it can also be 1/2 if it's bound to fluorine. All right, and then so the other part of this with the nonmetals, we got hydrogen, oxygen, and then for the halogens, let's put another page in. Halogens are -1 for fluorine. These are oxidation numbers, -1 and -1 for the other halogens. Halogens are in group 7. So fluorine, chlorine, bromine, iodine. And then if a halogen is with oxygen, it can have a positive oxidation number. So you got elemental substances have oxidation number of 0. Monatomic ions have oxidation number of whatever their charge is. Nonmetals for hydrogen is +1 with a nonmetal, -1 with a metal. Oxygen is -2 if it's bonded to another atom, -1 if it's bonded to itself, and 1/2 if it's bonded to fluorine. And then for the halogens in group 7, right, it's -1 for fluorine and other halogens. And then with oxygen, the other halogens can have positive oxidation numbers. And then the last rule for assigning oxidation numbers is this. If you have a polyatomic that has a charge, that charge is equivalent to the sum of the oxidation numbers of all the atoms in that polyatomic or in that molecule. Let me start with the charge. So the charge on a polyatomic all right, so the charge on a polyatomic is going to be equal to the sum of all the oxidation numbers of the atoms that make it up, right? And this is important when we're looking at trying to calculate the oxidation number, right? And so we're gonna talk about it in kind of in 2 ways, because in one sense, if you have a salt or if you have 2 elements together, 2 atoms together, and you know what the normal oxidation number is for that atom or element in the group based on the group that it's in, you can think about this more than one way. So let's look at both ways. Well, we need to know how to do it both ways, so we're going to look at both ways. Right, and this is important. Again, this is a skill set that we're developing for a concept that we're going to walk right into in determining whether a reaction was an oxidation reaction or a reduction reaction. Right, we're developing this skill set so we can apply it to something. All right, so if I have a compound like this, right? One way to think about this is to rip it apart. If we look at it as it's not a salt, it's a covalent compound. But if we think about it like we thought about putting the compounds together using the crisscross method. If I undid this and pulled it apart, what would I have? What would the charge be on hydrogen? Right, we know from the rules that if hydrogen is bonded to a non-metal, the charge is going to be +1. The oxidation number is going to be +1. But if I pull this apart, if you remember that crisscross method, if I pull this apart, where's that 2 going to go? That subscripted 2.
To the other side?
To the S.
To the S. Good, 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 good. Other side, I'm assuming that means the sulfur. So you're right. So if I pull
Yes,
this
sir.
apart, that's going to be +1. And then the S is going to be what? -2. Following? Because if we crisscross them, that's what we would get H2S. But there's another way to think about this. This is one way to think about it. It is really a shortcut method that we're going to apply to a couple of other examples. And then we're going to compare it. What we'll find out is we'll get the same thing. So to calculate the oxidation number of any element within a molecular compound, right, or any atom within the molecular compound, we need to know that the overall charge is whatever that compound is. So here, this is neutral, right? There's nothing up here. There's no +1. There's no -3, none of that, right? So it's neutral. So we're going to set that overall charge as 0. And we're going to find.
I have a question.
Go ahead.
So does it not matter that one of them is 2 and one of them is +1? I mean, yeah.
You mean over here on the when we pulled it apart?
Right.
Yeah, it matters. But what we're getting ready to show is that we can calculate that and get to the same conclusion. If that makes sense.
Okay, that makes sense. Yeah.
This is a kind of a shortcut method of doing it, but I'm also going to show you how to calculate the oxidation number. All right. So we know from the overall, so the oxidation number, will be considered a polyatomic. It's got more than one atom in it, and the charge on it is 0. So rule number 4 says that the polyatomic charge is equal to the sum of the oxidation numbers. So that's how we're thinking about this. So I'm going to make that the overall charge, which is 0, and I'm going to set that equal to the number of atoms and the oxidation numbers that we know. So for hydrogen, right, we know that we have 2 hydrogens, and we know that the oxidation number for hydrogen, based on the rules that we just went over, is going to be +1 if it's with a non-metal. Everybody following that?
Yes, sir.
Mm-hmm. And then we're going to add, this is a sum. So we're going to say for sulfur, if we don't know it, because let's say, for instance, we don't know it, we're going to just make that X. And all we're going to do now is solve for X. So this is the oxidation number for hydrogen. And this, we're solving, is going to be the oxidation number excuse me, for sulfur. All right, so that's going to be, we're going to take this and just solve for X. So 0 is going to be 2 plus X. And if we solve for X, it's going to be -2 equals X. Is that right? We just move this over on this side. It's positive on the right. We move it over to the left, it becomes negative. So now this is the oxidation number for sulfur. So we did the shortcut method, we saw that, but we also need to be able to calculate it. And the way we calculate it is to set the overall charge for the polyatomic, which is 0, equal to the sum of the oxidation numbers that make up the polyatomic. All right, so we had 2 hydrogens with a +1 charge. We were solving for sulfur, and we found out that sulfur is -2. And that makes sense, right? If X is -2 and H is +2, the overall charge should be what? 0. Is that right? If I go back in and put that -2 in where X is, I should get 0, which is what we got. Any questions about that? All right, let's do another one. Let's take potassium nitrate. And let's solve for nitrogen. Let's figure that out. Now here, you could actually take the nitrate if you chose to, pull it apart, and find out what nitrogen is. But here we're going to solve, we're going to keep everything together and solve it that way. Because if we pull this apart, this would be K plus and then NO3 minus. Is that right? That's the charge on a nitrate. Polyatomic is -1. And we could solve for N. If we just took NO3, we could solve for that. But I want to keep it all together to make a point, right? So K, we know that potassium is +1. It's a monatomic ion. We know that this is a salt because the potassium is a metal. The nitrate is a non-metal polyatomic. So potassium is in group 1, so it's going to have a +1 charge. So we know that this is a monatomic with a +1 oxidation number. And we also know that oxygen, based on the rules, if it's in a bond with another atom, we're going to have an oxidation number of -2. Right? Everybody okay so far? And the salt,
Yes, sir.
the salt itself has an overall charge of 0 because it's neutral. So we're gonna solve this like this. We're gonna make it 0 for the overall charge, which is gonna come from the sum of all your oxidation numbers. And then we're gonna say for potassium, this is gonna be 1 times +1, right? And we're gonna solve for nitrogen, so plus X. And then for oxygen, let me move this up some. This is the beauty of teaching virtually. I love being able to do that and not having to erase the board or whatever. All right. So N we're solving for, and then O, let me give you a quick piece of advice here. So we got 3 oxygens based on the subscript. That 3 is only for oxygen. It is not for nitrogen. The only time we distribute a subscript through is if it's outside of the parentheses like this. That's the only time we're going to distribute that. But that 3 and NO3 does not get distributed. All right, so that's just for oxygen. So we're going to say O is 3 times, what's the oxidation number for oxygen if it's bonded to another atom? Based on the rules. Right, it's -2. So we're going to take what we know and solve for what we don't know. All right, so over here, we're going to say that this is 3 times, and the charge does matter, -2. All right, so this is going to be 1 plus X minus 6 equals 0. That's going to be -5 plus X is 0. So all we got to do now is solve for X. Just move that, add that to both sides. Right, so it'll be +5 equals X. So the oxidation number on nitrogen is +5. Following? Yes, no?
Yes, sir.
All right, any questions? All right, so what do we do with this information? If we go back and put those numbers into that top equation where we set it up to equal to 0, then we'll notice that we'll get the whole thing should add up to be 0 because it's a neutral compound. The other part is, if you notice here, oxygen has an oxidation number of -2. And if you look on the other side, so did sulfur. And if you look at the periodic table, you'll see that oxygen and sulfur are in the same group. So groups, normally the atoms in a group are going to have that same oxidation number for especially for non-metals. For metals, it's a little bit different because the transition metals can have different oxidation numbers. We've already seen evidence of that. All right, let's do one more example, and then we're going to move on to applying this. All right, because we're still talking about redox reactions, oxidation and reduction. All right, so we're going to take this H2 PO4 minus, and we're going to solve for P. All right, we're going to solve for P. And keep in mind, we see here the overall charge is not 0, it's -1. So whatever we put together in our equation for all the atoms, we're going to set it equal to -1. What do we know about oxygen already? What's the oxidation number for oxygen if it's bound to another atom?
-2.
-2. What about hydrogen if it's with a non-metal? Oh, gave it away.
1.
Yeah, good. I gave it away, but yeah, you're right. Oxygen is -2. We already know that based on the rules. And then P, we're going to solve for. All right, so it's going to be a 3-term equation. And we're going to set it all equal to -1 because that's the overall charge on this polyatomic. So -1 equals, for hydrogen, we're going to say 2 times +1 plus X for P. So this is H, this is P, and plus 4 times -2 for oxygen. Again, let me go back and restate what I said a second ago. This 4 right here does not distribute. Right? That's strictly for oxygen. It has nothing to do with phosphorus. The only time you would distribute a number through a polyatomic like that is if there was a subscript out here. Then both would get, be distributed. That subscript would be distributed to both. But because the 4 is strictly with oxygen, it does not distribute. Let me just put a little note right here. Right, because somebody may not have said it, but you may have thought it. So I'm trying to catch that. All right, so this is -1 equals 2 plus X minus 8. Is that right? Because that's +4 and -2. And so we combine these two, we're going to get -6 plus X equals -1. And then if we add 6 to both sides, we'll get +5. That plus sign is horrible. It's equal to X. So the oxidation number on phosphorus is +5. All right. So can somebody look at the periodic table, if you have one close by you, and tell me what group phosphorus is in? Now, if you look at the periodic table, phosphorus and nitrogen. Hold up, see it in the chat. I see a chat. Okay, it's actually group 5. All right, but the 5 part is right. I get it. So boron is group 3, carbon is group 4, oxygen is group, I'm sorry, yeah, 3, 4. Nitrogen is group 5, and then oxygen is group 6, and then your halogens are group 7. So it is a group 5 element. And if you notice, up here when we saw for nitrogen. Nitrogen was also group 5. So again, the elements that are in a particular group, if they are involved in, you know, the formation of a polyatomic ion, then the oxidation number is usually going to be the same for all the elements in that group, especially if it's a non-metal. All right. So with that being said, now we got another way to think about oxidation and reduction. We talked about redox being, or redox reaction. One way we said was gaining and losing electrons. So gaining was oxidation, losing was reduction. Now we can expand this definition, right? So now we can say that a redox reaction happens when one or more of the elements undergoes a change in oxidation number. And this is an important definition because sometimes you can't see when the oxidation number changes. So it's good to be able to check it. Right, so that's another more expansive definition of reduction oxidation, right? Where one or more of your elements undergoes a change in oxidation number. All right. And so again, that's connected, right? So if the oxidation number goes up, if it increases, that means that something has been oxidized. If it goes down, that means it has been reduced. And the way you make the oxidation number go up is to lose electrons. That's what oxidation is. The way you make the oxidation number go down or reduce it is to add electrons, right? So now we're going to look at a couple of examples of determining whether or not something is a redox reaction, right? And that's important because we need to be able to to say whether or not a reaction is a reduction, oxidation reaction or not. And the way you tell that is this: in a redox reaction, one or more elements is going to have a change in oxidation number. So on the starting material side or the reactant side, you're going to have specific things reacting together, substances reacting together, and they're going to all have specific oxidation numbers. When you look on the other side to the products, if that oxidation number changes in any one of those substances, then you know that you had a redox reaction to occur. All right. So let's look at that. We're going to actually finish up here between the examples I'm going to show you, the initial examples and the other examples, where we're going to have to determine it either by calculating the oxidation number or using our little shortcut method if we know we have a salt. So let's do that. So let's take in the first example, we're going to determine if a redox reaction happened. Right. And again, what we're looking for is, did the oxidation number change from in the start material, from going from reactants to products? So in the first example, let's do this. Let's take zinc metal plus 2 HCl goes to Zn, or zinc 2 chloride plus hydrogen gas. All right, now let's look at that. Right, and it is balanced. The next one I'm not going to balance. I'm going to, because I still want to keep working on that skill. We can never get away from balancing ever in life, period. All right, at least until you get out of GChem part 2. So from now until the end of GChem part 2, you will never not see a balanced or unbalanced equation that you'll have to balance. So if it's unbalanced, you got to balance it. If it's balanced, then you got to use those numbers for something. All right, so zinc is elemental in this case. What do we know about elemental substances and their oxidation number? What is the rule for that? If it's elemental and it's not an ion, the oxidation number by default must be 0. Has to be. That's the rule. So if zinc is in its elemental form, then it has oxidation number 0. All right. And then if we look on the other side, zinc is no longer elemental, it's actually ionic. What happens if we rip that apart? And we can do this both ways, by the way. And I think we will, just for the sake of, for clarity, right? What happens if I rip this apart into its ions? What do I get? Look at the subscripts. This is understood to be 1. If we uncrisscross it, if we undo it, where does that 2 go?
To the zinc, and then chlorine, or is that chlorine?
Mm-hmm.
Well, that one will be 1.
So 2 plus, and then Cl minus 1. Is that right? And we're going to put a 2 here to keep that, to stay, true to that. Keep the integrity of the of the atoms that are in that compound. Right? So let's look at this. Now, this is, again, we're applying a shortcut because we have a salt on the other side that we can easily observe and determine whether or not zinc got oxidized or it didn't. Right? So let's look at what happened. So zinc, in this case, went from what? 0, is that right? To what? Plus 2. Yes or no?
Yes, sir.
So what happened to it? Did it get oxidized or did it get reduced? Let's think about it. The oxidation number went up, right? And so if the
Would it be reduction?
No, it would be the opposite. If the oxidation number increases, that means that it has been oxidized. If it decreases, that means it's being reduced. All right. Does that make sense?
Yes, sir.
All right. So zinc got oxidized. All right. What does oxidation mean again? What's another definition for that besides the oxidation number going up? What's the other definition? Is it losing electrons or gaining electrons?
Losing, right?
Losing. So how many electrons would zinc have to lose to go from 0 to plus 2 if every electron has a -1 charge?
Three.
All right. If every electron has a -1 charge, I'm with you, because you're starting at 0. I feel it. But let's say we go from 0 to +1 and then +1 to +2. Right? So we're starting at 0 and then we lose 1 electron, that'll leave us at +1. If we lose another electron, then that'll leave us at +2. Are you following that?
Yes, sir.
Mm-hmm. I understand your answer though, because you're counting from 0 to 1 to 2, and that's an increment of 3. But here with the charges, if the charge is 0 and we lose 1 electron, that charge is just going to go from 0 to +1. So the oxidation number increased and we lost 2 electrons. All right. So zinc got oxidized. Here's the rub. Anytime we do a redox reaction, if something gets oxidized, then something else has to get reduced. So let's see if we can figure out what got reduced. So let's look at the chlorine. Right here, if we pull this apart, this is going to be, let me use a different color. This is going to be 2H plus, is that right? And then what? 2Cl minus, because that 2 is going to be used to as the coefficient for both atoms, because it gets distributed, right? So this is H plus over here, and then over here, you can see that chlorine is what? It's also what? Minus, is that right? So over here is -1, over here is -1. So chlorine, nothing happened because the charge didn't change. The oxidation number didn't change. It's -1 on the left in the reactants. It's also -1 in the products. But if we look at hydrogen, it's +1. Hydrogen is +1 here. But on this side, what is it? It's elemental. So what is the charge there?
2.
It's 0. Is that right? Any elemental substance is going to be 0. So the charge here is 0 on that molecule. Is that making sense at all?
Yes, sir.
All right. So now what happened to hydrogen? It went from +1 to what? 0. Yes. So this went from +1 on the reactant side to 0 in the product. Did it get reduced or oxidized? This is by default. If zinc got oxidized, then whatever the other process, the reduction part, the other atom, whether it would have been chlorine or hydrogen, had to be reduced. So the hydrogen, sorry about that. The setting is too thin on the pen. It got reduced. So the oxidation number actually went down. So it went from +1 to 0. And it got reduced by 2 electrons. Also another very important concept, because the oxidation and the reduction, the number of electrons is going to have to be equalized at some point. In this case, both either gained or lost 2 electrons. So that's fine. But in some cases, that's not always going to be true. So you have to equalize it, which we'll talk about on Wednesday. Any questions about this at all? All right. What if we took and let me do this last example, and we'll start out Wednesday with another example, because I don't want to go too far over time. Depending on how fast we get through this, I may be able to squeeze in one more example. So let's say we have copper plus silver nitrate, a reaction that you're going to do at some point. Actually, if you're in the Wednesday lab, you're going to be doing this reaction Wednesday, I think. No, Tuesday, tomorrow. The Tuesday lab folks are going to be doing this stoichiometry reaction, where you actually do a single displacement with copper sulfate and iron metal, to give you iron sulfate and copper metal. It's a cool reaction, because you get to see that elemental copper forming. But anyway, I don't want to take up all the time with that. You'll see it tomorrow if you're in Tuesday lab, and then if you're in Wednesday, you'll see it next week. So that's that, and then it's going to give me elemental silver, which is a solid, plus copper 2 nitrate. All right. Now, question: is this balanced? Let's go through all of our little check boxes. Is this balanced? It has to. If it's not balanced, that's going to throw everything off. And if it's not balanced, I need a volunteer to balance it, or tell me how, at least tell me how to balance it.
There's 2 of the NO3 on the other side, on the left side. So, or sorry, right side. So it needs to be 2 on the left side as well.
Put a 2 right there.
Yes, sir. And then
Alright.
that you need to balance that on the other side for the AG.
So I need to balance the silver by putting a 2 right here. Excellent. Nice work. And that'll put us in harmony. Everybody's happy. All right. Now let's see if we can figure out what happened. So silver over here, we break this apart. Come on, Russell, tighten up. This is AG plus, and that's 2 of those, plus 2 NO3 minus. Is that right? And then this is going to elemental silver, which we know is what? Any elemental substance has an oxidation number by default of what?
Zero.
0. Excellent. So the oxidation number on any, if it's an elemental substance, not an ion, is 0. But over here is +1. So what did it do? Did it get oxidized or did it get reduced? It went from +1 down to 0.
Reduced.
It got reduced. How many electrons did it take to reduce it? Let's just take, because see the coefficient, we got 2 silvers. So let's just say for one of those silvers, if I want to go from +1 back to 0, how many electrons are involved in that process? If the charge on an electron is -1.
1.
1. Good. Now, is it added or is it subtracted? That's what knowing the terminology, knowing what reduced means, that's where that comes in. If it's reduced, that means I've added electrons. So I've added 2 electrons, right? Because I got 2 silvers and each one of them is going to pick up an electron, right? And to give me those 2 elemental silvers on the other side. So I added 2 electrons. Are y'all following? Does that make sense? Both
Yes, sir.
silvers are +1 on the reactants, and then they both of them are 0 in the product. So each one of them picked up an electron. So I have a total of 2 electrons added.
So does that mean that since this was reduced, then the other components will be oxidized?
Come on with the come on. That's exactly what it means. So the copper, we can see here the copper, if we break this apart on this side, uncrisscross it, undo it, this will be copper 2 plus, and this will be 2 NO3 minus. Is that right? So we just worry about the,
Yes, sir.
we keep the, the coefficient. Excuse me. I just ate, so I apologize for that. We keep the coefficients. So this is 2 plus, and the copper started out, it's elemental, so it's what? 0. We know that. So what happened to copper? Copper went from 0 to 2 plus. So that was, you just said it, but I just want to reiterate it. That copper in this case got what? Oxidized. Is that right?
Yes, sir.
And because it got oxidized, and because it went from 0 to 2 plus, how many electrons did it lose? Because oxidation is the loss of electrons, like reduction is the addition of electrons. So how many electrons did it lose going from 0 to 2 plus?
2.
2. Good. Don't be scared. 2 electrons got lost, right? Because every electron has a -1 charge, and every one you lose, the charge goes up by 1. Right? I remember when we talked about atoms and ions and elements, and we kind of touched this already, right? When we talked about the atomic number being the number of protons, And then if it's an ion, it's got the same number of protons, but a different number of electrons. So the charge is dictated by the electrons being either given or received. So if it gets reduced, the charge is going to go down. If it gets oxidized, the charge is going to go up. So we're going to stop right here. We'll pick up with another example on Wednesday, and then I'm going to send you, hopefully I'll finish it today. I'm going to send a video out about how to balance redox reactions. So when we come back on Wednesday, we don't come back cold, right? We'll already have an idea of what we're jumping into. But I got to finish making it first, which I'll do when I get off of here. And after I send you all the notes and all that stuff. All right, so we're going to stop here.